So there is a wrong order of the slide, but you can find them all in here. Okay, so right now we focus on fading channel. What we have seen so far is an analysis, very quick analysis of additive wide Gaussian channel, in particular evaluation of error probabilities, capacity on the Gaussian channel. Now we move to fading channel. Essentially, we parallel what we have seen in additive wide Gaussian channel by increasing the complexity of the model, in particular introducing fading. So I will start with a quick introduction to modeling the fading. Then once we have a mathematical expression for the fading, we see how we can demodulate or decode on the fading channel, what is the error probability for a coded system on the fading channel, and what is the capacity for a fading channel. So everything is going, in a sense, in parallel to what we have seen for the Gaussian channel. So let me start with the model for a fading channel. Fading channel, generally a wireless channel, is affected by additive wide Gaussian noise, just as the channel that we have seen before, plus a few things that can be categorized as path loss, shadowing due to obstructions between the transmitter and the receiver, and multipath fading. It consists of, it is the effect of two things, the combination of two things, multiple reflections and movement. So we shall analyze these things, in particular multipath fading, in order to arrive at a mathematical expression for the input-output relationship of the channel. So let's consider a channel in which the red martini glass is a transmit antenna that transmit power PT, and PR is the power received by receiver, which in general is in motion, relative motion with respect to the transmit antenna. The first effect that we have to take into account due to this movement is the path loss. In the abscissa, we have time, or if you prefer, distance, because the velocity includes the velocity of this receiver implies that the distance increases or decreases with time. And consequently, we have that the power that we receive as divided by the power that we have transmitted in dB, at least in principle, decreases with time, with a linear law as a simplified model. So this is the path loss, and it changes the ratio between the transmit power and the receive power. It changes relatively slowly. Second effect is shadowing. This occurs when we have obstacles between the transmitter and the receiver. For example, trees that shadow the base station once we are receiving the signal from it. And the variation of the received power with time due to shadowing is generally slower than the variation, faster than the variation due to the path loss. And we say that the shadowing effect is slow fading. And this causes a fluctuation, in general a random, we have to model is a random fluctuation of the received power with respect to the transmit power that goes more or less like this. Then we have a fast variation that is due to the multipath fading, due to the fact that even small variation in the geometry of the propagation path may cause considerable variation of the ratio between the received and transmitted power. Consequently, the combination of path loss, shadowing, and multipath fading, the fast part, may look like the one that we have in this graph. A very quick variation of the ratio between received power and transmit power with time or with space. Okay, how do we model these effects? The simplest possible situation occurs when we have a line of sight path, where there's no obstruction, no obstacle between the transmitter and the receiver. The transmission occurs in free space. and consequently the ratio of between the transmit power and the receive power is proportional to, well, actually PR divided by PT, but anyway, it's proportional to D minus 2, and proportional to the square of the wavelength of the transmission, or we prefer inversely proportional to the square. Again, there is a misprint here. That should be ratio P, the receive power divided by the transmit power. And you see the distance, you can think of variation in terms of distance here or in terms of time if we assume that there is a constant velocity of the receiver with respect to the transmitter. The standard law that we assume for the path loss is the ratio between the receive power and transmit power to be d to the minus alpha. In free space, alpha is equal to 2. In practical environment, alpha may be something different. Okay, one might observe that this law is valid only for far field because, for example, if take alpha equal to 2, for example, saying that we have a relationship between receive power and transmit power of this form, PT divided by PR equal to a constant divided by D square, does not mean that when the distance is 0, the ratio becomes infinity, right? Sorry. So if we model, if we do a simulation or calculation, if you want to model the path loss using the formula like this, make sure that you are considering that only the far field effect. Otherwise, some people prefer using 1 over 1 plus D square, which means that the relation goes like this. So here P received equal to transmit power when D equal to 0. Okay, so don't be fooled by the usual assumption that this expression holds. This expression holds only for far field. Okay, so this is the usual assumption. Alpha is equal to 2 in the free space. Alpha is something different in practical system. Again, free space alpha is assumed to be equal to 2. For cellular radio urban areas, it's assumed that alpha ranges from 2.5 to 5, which means that there's more attenuation due to distance in this environment. In enclosed area of line of sight, the attenuation is smaller than the free space, 1.6 to 1.8. And in enclosed area and with blocked propagation, then attenuation will be larger from 4 to 6. This does not mean that the alpha is exactly like this and takes exactly this value in all propagation conditions. If you measure the variation in between the received power and the transmit power, that is the attenuation, as a function of the distance between the transmitter and the receiver, you may end up with experiments that lead to values that are spread around a certain line. But the usual model is to assume that alpha is a constant, and consequently all these experimental points are conceptually gathered on this straight line. How about shadowing? Shadowing, as I said before, model the attenuation that we have from the obstruction, an obstacle separating the transmitter and the receiver. Being unable to do an exact modeling for shadowing, we resort to statistical model. Statistical model does not mean that the shadowing is actually random. It simply assume that we are not able to model exactly the effect of shadowing, and consequently it's convenient to assume that the attenuation is a random variable. And due to the fact that the number and the type of obstruction cannot be told exactly. And the usual assumption about shadowing is that it follows, the attenuation follows a log normal distribution. In other words, the dB, the decibel value of the attenuation, is a normal, is a Gaussian random variable, with two parameters that define as the Gaussian, the mu, the mean, and the variance sigma square. And it's usually assumed that mu is equal to 0 because the mean value, which is non-zero in practice, but it can be captured by the path loss. And the variance ranges roughly between 4 and 12, but again, it has to be measured, and consequently, it's an empirical value. One may connect this concept of shadowing and path loss to some practical concept like cell coverage or outage probability. I'm going to discuss outage probability later on, but for the moment we may just comment on the fact that this outage probability is the probability that we receive a power from the transmitter that lies below a certain minimum, the minimum value that is necessary for reliable transmission. This is called an outage probability. If we had only path loss, then the shape of a cell, in other words, the shape of a region in which we receive the same amount of power, or the minimum power, we receive the minimum power, we don't have outage probability, would be circular. So inside a circle, we would get the power that we need to avoid outage. With path loss and shadowing, that you cannot say anymore that the cell has a circular shape, and we might have this amoeba shape like this, or something, random shape in a sense. Okay, multipath fading, as I said before, is generated by the combination of two effects: the reflection, the fact that the transmitted ray, let's call it this way, does not reach directly the receiver, but may be reflected by the ceiling, by the ground, by the walls of a room, and things like that. And movement, and the fact that we have a relative movement between the transmitter and the receiver. It's the combination of these two factors, the reflection and movement, that generate multipath. And I'm going to show it to you in a couple of simple examples. So again, we have to consider separate reflection and movement, and then we combine them together to show that we have the fluctuation, and possibly very fast fluctuation, of the received power with respect to the transmit power. Okay, consider the simplest possible case of a reflection, the so-called two-ray model. We assume that from the transmit antenna to the receive antenna, we have two paths, one direct path and one path that is obtained by a single reflection on the ground. This means that the received signal y of t, if we call x of t the transmit signal, with after compensating for the amplitude and the delay, combines a direct ray, this one, that would be x of t, with again with an amplitude that we assume to be 1 and the delay we assume to be 0, and the reflected ray. So b is the relative amplitude of what we receive through this reflected path, and tau is the relative delay. So we have a combination of two signals. What's the effect of this combination? The effect of this combination is that the channel can be modeled as a linear time invariant channel with a transfer function given by this expression, h of f is equal to 1, that corresponds to the direct path, plus this term that corresponds to the reflected path. B again is the relative amplitude of the reflected path, and tau is the relative delay of the reflected path. The result is that, slightly exaggerating the figure for purpose of illustration, the effect is that the magnitude of h of f has a fluctuation. Okay? That means that we have a distortion of the transmitted signal according to the bandwidth of it. So, if it occupies a small bandwidth, then we may have no distortion. If it occupies a wide bandwidth, then we may have a considerable distortion because of the variation with frequency of h of f. We have these notches that are small values, correspond to smaller values of h of f. Now let's move to effect of movement. So we have seen that the effect of a reflection is that of potentially distorting the signal transmitted because of the variation of the magnitude of the transfer function of the channel. So we have a distortion. But the channel is linear and time invariant. Now let's consider the effect of movement. Effect of movement causes what is called a Doppler shift. Assume that we have a receiver that moves away from the antenna with a velocity v, and the signal, a sinusoid for simplicity, at frequency f0, leaves the transmitter and reaches the receiver at an angle gamma. The result is that the Doppler effect says that the frequency that is received by this receiver, moving at velocity v with an angle gamma, is affected by a Doppler shift. Instead of receiving f0, the same frequency of the sinusoid that was transmitted, we received f0 minus fd, where fd is given by, is proportional to f0, is proportional to the velocity of the medium, is inversely proportional to c, the speed of transmission of the electromagnetic field in the medium, multiplied by the cosine of gamma. So this fd may be either greater than 0 or less than 0 according to the direction of the velocity. If the receiver moves away from the transmitter, then fd is positive, otherwise it will be negative. Okay, now let's combine together the effect of movement and of reflection. The simple possible case occurs when we have only two rays and a receiver that moves with velocity v. Okay, so we receive two signals here, one from this path, this one, okay, that is affected by a Doppler shift. So if A is the amplitude of the signal, we don't consider variation in the amplitude for simplicity, and we have transmitted the sinusoid at frequency f0. From this path, we receive a sinusoid at frequency f0 multiplied by 1 minus v over c, Doppler effect. But we also receive a reflected path. So we receive it here at an angle gamma with respect to the direction of movement. This means that the Doppler shift that affects the signal received from this path will be 1 minus v over c multiplied by cosine of gamma. Okay, so we have two paths, one corresponding to the frequency f0, 1 minus v over c, and the other one corresponding to f0, 1 minus c cosine gamma, simply because we receive the signal under two different angles. What's the effect? I mean, if we combine together these two signals, we discover two things, that we transmit one tone, f0, and we receive two tones. This immediately tells us that the channel is not linear and time invariant anymore. It's something different that can be analyzed using standard techniques for non-time invariant system. But what we want to focus on in this case is the fact that the received signal does not have a constant amplitude anymore. We transmit a sinusoid and consequently a signal with a constant amplitude, and what we receive is a signal whose amplitude fluctuates. And the fluctuation reflected by this envelope that I call capital R of t reflect the fact that we combine together the movement and the reflection. The reflection alone does not cause a variation in the amplitude of the sinusoid. It's the combination of the movement and of the reflection that causes a fluctuation in the amplitude. If we want to compute the envelope, we discover that the variation on the envelope depends on f0, of course, and the 1 minus the cosine of gamma. But the interesting thing is that we actually have a fluctuation in the amplitude, something that we wouldn't have with reflections alone. It's the combination of reflection and movement that causes a fluctuation in the envelope. Now let's consider the most realistic case in which we have movement and multiple reflection. We have several obstacles all around the receiver. We have obstacles, and we receive a large number of rays, of signals from different paths. And each signal will have a different amplitude due to the fact that they follow a longer or shorter path, and arise with a different angle because of the geometry of the propagation. How can we model it? For the two simple cases that I've been considering so far, it was simple to write down a deterministic expression for the received signal. In this case, we cannot, because the situation would be too complex, and in addition, it's time varying, because as the receiver moves a little, then the whole geometry of the propagation changes, the phases of the signal change, and consequently we are not able to write down a deterministic equation that tells us what's going on. So typically in science, whenever you are in a situation like this, situation in which we are not able to model exactly what's going on, you resort to statistics, to a probabilistic model. So this is what they do. The received signal turns out to be a sum of a very large number that we call capital N of sinusoids, each one having its own attenuation, each one having its own Doppler shift, frequency shift, each one having its own phase shift. Okay? So we are in the presence of a equation, input-output relationship that depends on a very large number of parameters that also change from time to time. We are unable to use it as a deterministic equation, so what we do is to resort to probability modeling. And we do this by observing that there is a very useful theorem in statistics, the central limit theorem, that tells us that whenever we add together a number of random variables that are independent or weakly dependent, and the result under very general conditions turns out to be a Gaussian random variable. So we use this central limit theorem to model multipath fading. So we assume that the amplitude of the received signal from time to time follows a Gaussian distribution. In particular, we observe that if we extract from this input-output expression the complex envelope, that is the quantity, the complex quantity that changes with time and multiplies the transmitted, the originally transmitted sinusoid, will be a Gaussian random process. The complex envelope is a Gaussian random process. So invoke the central limit theorem and conclude the complex envelope is a Gaussian random process. So we are led to the consideration of a Gaussian model for our fading. The assumption again is that the number of rays is very large, theoretically close to infinity, and all contributions are statistically independent, but the model works well in reality. So multipath fading will consist of the effect on a transmitted sinusoid, that is a sinusoid that has constant envelope and constant phase. What we get is a sinusoid that have a random phase and a random envelope. We'll see that the envelope is plays a more important role than the amplitude in terms of the fluctuations. So if the R of t is Gaussian, if the complex envelope is Gaussian, should be here. Okay, is Gaussian, and the mean value is 0, then the envelope, the magnitude of that complex Gaussian random variable is Rayleigh distributed. That's a simple exercise in probability theory. That is, we can model the envelope of the fluctuation at any given time by using a Rayleigh random variable. That is a random variable that has a probability density function of this form. r over sigma squared, the variance, multiplied by e over minus r squared divided by 2 sigma squared for r from 0 to infinity. And this is the probability density function of a Gaussian with a Rayleigh random variable for example, for sigma squared equal to 1/2. So this is a very common model. It occurs whenever we may assume that the complex envelope of the signal that we receive is a Gaussian with mean 0 at a variance sigma squared. We have that the expectation of r squared, the expectation of the power of the envelope by computing the simple integral is equal to 2 sigma squared. And consequently, we can normalize the fading power to 1. This is a very common normalization, and assume that the probability density function of the envelope is equal to 2r to minus e to r minus r squared. That's the normalized Rayleigh fading. That's the very common for calculation. So when we have we accept the assumption that the envelope is Rayleigh, then we may normalize the fading power to 1 and use this density. In some cases, we are not allowed to say that the envelope, which is assumed to be Gaussian because of the central limit theorem, has a mean 0. And this occurs, for example, when we have a number of so-called weak paths that come from reflection and the direct path that come from an unobstructed transmitter. Occurs, for example, for satellite transmission with a satellite high above. In this case, we may not assume that we have a 0 mean for the Gaussian fluctuation of the complex envelope, and instead of having a Rayleigh model, we have a Rice model. Rayleigh is the density of the a magnitude of a 0 mean complex Gaussian. Rice is the density of the envelope of the magnitude of a non-zero mean complex Gaussian. And this is the mathematical model, more complex than beforehand. Anyway, it's a probability density function called as Rice density or Rician density r over sigma squared exponential and I0. This is the Bessel function, the modified Bessel function of first kind and order 0. And here we have an additional parameter, as we see, for a Gaussian, for a Rayleigh random variable. We have only one parameter, sigma squared. Here we have two parameters, sigma squared and v squared, which is the amplitude of the deterministic path, the unobstructed path. This has no fluctuation, so it's deterministic. And this is the power that we transmit from the the deterministic, the unobstructed path. So this is another convenient model. The fading power of the Rician fading is given by v squared, the power of the direct path, plus 2 sigma squared, the power of the Rayleigh component. Okay. And consequently, we may normalize the whole thing by first defining what is called a Rice or Rician factor, which is the ratio between the power of the unobstructed path and the power of the diffuse component, of the Rayleigh component. Remember, we have two basic components here, the direct component coming from here, and the reflected set of components. These are Rayleigh, and this is deterministic. The combination of the two yields the Rician model, Rician density function for the fading. Okay, so we define this Rice factor. This is a very important parameter, the ratio between the deterministic part and the random part, if you want to interpret it that way. And we can normalize the density by using this Rician factor. So this is the most common expression that you will see around for the Rician density function. And essentially the exponential as before and the I0 function as before, but this is expressed in terms of this Rice factor. This is the Rayleigh, and these are the possible values of the Ricean density function with different values of k. You may notice that as k increases, this curve moves to the right, and it looks more and more similar to a Gaussian density function. This is the truth. This is exactly what happens. You can see it also mathematically. Limiting case is k tending to 0. Remember that k is the ratio between the deterministic component and the random component. If k goes to 0, means the deterministic component disappears. We only have the Rayleigh component, the diffuse component. So in this case, we have a Rayleigh. So Rayleigh is a special case of Rice when the mean value is 0. The other limiting case occurs when k grows to infinity. Remember that k is a ratio between the deterministic and random. So k growing to infinity means that we have no random component, and consequently we have only deterministic component, and the Ricean distribution becomes a Gaussian distribution. It tends to an additive wide Gaussian channel, albeit with a very large mean value. So that means in particular then if you want to analyze the effect of fading on a certain system, then you may observe that typically Rayleigh and Gaussian are two limits, you know. Always work worse than the Gaussian and better than the Rayleigh. And Ricean factors take into account the space in between the Rayleigh performance and the Gaussian performance. We'll see some curves like that. Now, remember now that our multipath fading takes into account the fluctuations, so it should model the fluctuation of a received signal. And so far, we have modeled the, here it is, one more. Here. So far, we have analyzed the first order behavior of this envelope and possibly also the phase. The phase is less relevant. Well, first order doesn't tell the whole story because it does not tell us how fast the fading changes, how fast this set of this amplitude vary. So we know that the probability density function, we can model the probability density function time by time. So at any given time, we can model the amplitude, and we say, okay, this is Rayleigh or this is Rice, or we may use a different model like a Nakagami, etc. There are many, but anyway, Rice and Rayleigh are the most commonly used for calculations. But we need more. I mean, we cannot model a random process by using only first order statistics. We need at least a second order statistic that tell us in a simple way how fast these fluctuations are. Unfortunately, modeling exactly the second order statistic of a fading is not an easy task, so we resort to some simple parameters, and the simple parameters that I'm going to describe you are the coherence time and coherence bandwidth of the fading, which are single parameters, so very simple to deal with, but on the other hand are very useful for to analyze, to understand what's going on. Remember, we are rather focusing on basic principles, not on a detailed analysis of a single situation. And in terms of basic principle, it helps, helpful enough to have the indication of what the coherence time and the coherence bandwidth of the channel are, because they give us information about how fast the fluctuations of the fading are. Okay, so let's move to the definition of these two quantities. Okay, so we want to know how fast the fading changes with time, and also if we look at the variation of the transfer function with frequency, we want to understand how fast are the fluctuation of the transfer function with respect to frequency. So we define two quantities, coherence time and coherence bandwidth. Again, these two parameters do not tell the whole story about the higher order statistics of the fading because these will be very difficult to do it, but they are significant enough parameters to be useful for practical applications. Let me define first the delay spread. So we assume that we are, for simplicity, we assume that we transmit a single impulse. Okay? What does the receiver get? The receiver, if there are several reflections, for example, in this room, in the ground, the ceiling, and the walls, the receiver, assuming large enough bandwidth, the receiver will get a number of copies of the impulse that has been transmitted with different amplitude according to the kind of the length of the path it is followed, and different delays according again to the length of the path. So we transmit one impulse, and due to the reflection we receive a group of impulses. We define delay spread as the duration of this group, in the sense the time difference between the impulse that we receive last and the impulse that we receive first. So this length is the delay spread. Well, there are more sophisticated definitions, but conceptually, if you understand this, you can generalize the this definition to the case in which instead of receiving a discrete set of impulses, you receive a continuum of impulses. Anyway, we define the coherence bandwidth of a system, of a channel, as the inverse of the delay spread. More than the definition itself, it's useful to understand the operational meaning of this definition. What is the coherence bandwidth? The coherence bandwidth is the frequency separation at which two frequency components of the transmitted signal undergo independent attenuation. So you transmit an impulse, you receive a group of impulses with different delays, different amplitude. This is the delay spread. And the inverse of the delay spread is called the coherence bandwidth. Okay. The practically operational meaning of this is, again, the frequency separation at which two components of the transmitted signal undergo independent attenuation. So if you have a transmitted signal whose spectrum looks like this, okay, the frequency component corresponding to this frequency and the frequency component corresponding to the frequency will undergo different attenuation in general. Okay? If these two attenuations are independent, then we say that the two frequencies exceed the coherence bandwidth of the channel. This tells us, if you think about it, this tells us how fast the fluctuation of the spectrum are. Because if the spectrum is very flat, then essentially the two components undergo the same attenuation. If the spectrum fluctuates very quickly, changes very quickly with frequency, then there is essentially no relationship, no deterministic relationship between attenuation of one component and attenuation of the other one. And the coherence bandwidth tells us how fast the fluctuation of the frequency spectrum are. The dual concept of coherence bandwidth is the coherence time. We simply change time to frequency, and we reinterpret things by changing the notion of time into the notion of frequency, just by duality. So if instead of considering time, we consider frequency, which means that we transmit a sinusoid, an impulse in frequency is a sinusoid, what we receive in frequency will be a set of sinusoids. Remember that the effect of the Doppler effect, the effect of Doppler, you know, it has a number of reflection and consequently a number of different delay, different Doppler shift, and consequently you transmit one sinusoid and you receive a bunch of sinusoids. We call this a Doppler spread. The difference in frequency between the sinusoid with the larger frequency and the sinusoid with a smaller frequency. Okay, it was the definition that follows. That would be the coherence time equal to 1 divided by the Doppler spread. And we can interpret this, again, changing frequency into time, and saying that the coherence time is the distance in time above which two time components of the signal undergo independent attenuation. Okay? So a smaller coherence time means that we have fast fluctuation of the signal. So the envelope of the signal will change very quickly. A large coherence time means that the fluctuation will be very slow. You see from a component like here and a component in here have attenuation that are not deterministically related. In this case, if the coherence time is large, you see that two time components different by the same time undergo essentially the same attenuation. Consequently, this is the effect of coherence time. So coherence bandwidth tells us how fast the variation of the spectrum are. The coherence time tells us how fast the variation of the time envelope are. So we have coherence bandwidth, the inverse of the delay spread, and this operational meaning. The Doppler frequency spread, as I said before, is just the dual of the delay spread, and the coherence time is defined as the inverse of the Doppler spread. Just think of the two definitions as dual of each other. Change time into frequency, frequency into time, and you have the two definitions. So based on this, which relates it tells us about the effect of the channel affected by fading, we can observe the following. Let's consider a transmission, and the transmission of a signal with bandwidth B sub x. Okay, this is the bandwidth of the transmitted signal. Let's call B sub c the coherence bandwidth of the channel. Remember, this is 1 over the delay spread. There are two limiting cases in which the bandwidth of the signal is much larger than the coherence bandwidth, or the bandwidth of the signal is much smaller than the coherence bandwidth. Let me show this using a simple figure. This is frequency, and this is the channel, okay? And the channel has this given coherence bandwidth. So we want to transmit over this channel. What's the effect of our transmission over a channel that has a certain coherence bandwidth? Well, if we transmit a signal whose bandwidth is rather narrow, like this, then we see that all components of the signal undergo essentially the same attenuation. So the signal is not distorted in frequency. If we transmit a signal that has a large bandwidth on the same channel, you see that there is a considerable distortion. So So this is a narrow band situation. This is a wide band situation. But how we distinguish between narrow and wide bandwidth? Well, we had to compare the bandwidth of the signal to the bandwidth, the coherence bandwidth of the channel. Okay, so narrow and wide depend on the actual value of the coherence bandwidth of the channel. This is a narrow band transmission. We don't need equalization because the signal is not distorted in frequency. In this case, you see that the spectrum undergoes considerable variation, and we need equalization. Okay, so this is the practical meaning of the concept of coherence bandwidth. If B sub x, well, we are talking about rules of thumb. You know, what happens if the bandwidth of the signal is 1.1 the coherence bandwidth? I mean, that doesn't make much sense because of the definition of the sort of rough definition of the coherence bandwidth. But we can say that if the bandwidth of the signal is quite larger than the coherence bandwidth of the channel, then the signal is subject to what we call frequency selective fading. We need equalization. Frequency selective fading means that we have distortion in frequency. If, on the contrary, the bandwidth of the signal is much smaller than the coherence bandwidth, essentially all components of the signal are affected by the same attenuation, which means that the signal is not distorted. We don't need equalization. Okay, so BC has this meaning to tell us if what we are whether we are transmitting is distorted in frequency or not. So the channel is frequency selective or not. Again, there is no such thing as a frequency selective channel. It depends on the actual bandwidth of the signal that we are transmitting on it. Dual concept. Consider the transmission of a signal, elementary signal with duration t sub x, and we transmit this signal on a channel whose coherence time is t sub c. This figure is still valid once we change time into frequency and vice versa. Okay, so if this is the, we have a certain coherence time. If the signal, the transmitted signal, is much larger, the duration of the transmitted signal is much larger than the coherence time of the channel, a situation like this, we see that the channel, the amplitude is distorted. The fluctuation of the fading affect its single waveform. If the signal duration is short, then we see that essentially there is no fluctuation in the amplitude. We say in the first case that the signal is subject to time selective fading. The second case, we say that there is no time selective fading. Okay, so based on this simple classification, we may analyze what happens in general. We suppose that we have a channel with a certain coherence bandwidth and with a certain coherence time. Okay, so we have possibility of choosing different signals for transmitting here, signal with different duration and with different bandwidth. Okay, the nicest possible situation occurs when the transmitted signal is shorter than the coherence time and the bandwidth is narrower than the coherence bandwidth. In this case, we don't have this selectivity effect. We have a channel that is called flat in time and frequency. Let me stress again the fact that there is no such thing as a channel flat. I mean, the channel is flat if certain conditions on the signal occur. Okay. The the worst possible situation occurs when the channel is selective in time and frequency. Okay, an example of a channel selective in time and frequency occurs for avionic communication. For avionic communication, we have very long reflection from the airplane to ground and vice versa, and we have a very large speed. And consequently, the value of TC and BC will be very small, and whatever we transmit essentially falls in this region. The intermediate cases are channels that are flat in time and selective in frequency, or flat in frequency and selective in time. If we are working in this area, then we may want to move down here by doing equalization. So if we do equalization, we compensate for the frequency selectivity, and we end up into a channel which is flat in time and frequency. The most common model, and the one that I'm going to use for the rest of the calculation and the analysis today and tomorrow, is the channel which is approximately flat in time and frequency. And I will tell you in a second what I mean by approximately. So this is the most common and most useful, at least for calculation, among the fading models. By no means the only one, of course, and by no means it meant to model all possible practical situation, but it's by far the most common. A channel which is frequency flat, possibly after equalization, and approximately time flat, which means that the fading is slow. I will tell you in a second what I mean by that. So we are not exactly here, but approximately here. So it's not flat in time. It means that we have some distortion of the time waveform, but the distortion is slow in a sense, that to be made more precise. Okay, first, consider a frequency flat channel. Okay, we are, again, consider separately these two assumptions, frequency flat and approximately time flat or slow. Consider first frequency flat. What does it mean? Frequency flat means that there is no frequency distortion, so there is no, in time there is no convolution between the transfer function of the impulse response of the channel and the waveform that is transmitted over it. And the standard linear time invariant system implies that there is a convolution between the output is the convolution between the input and the impulse response of the channel. In this case, frequency flat means that there is no convolution. Instead, the fading, this Gaussian process with R either radio or rise, affects the transmitted signal multiplicatively. There is no convolution in here. A convolution would mean a channel which is not frequency flat. So frequency flat means that there is a multiplicative effect of the fading. So we have noise as usual, the transmitted signal x of t, and the transmitted signal is affected by fading in this way. This is a Gaussian process with R, Rayleigh, or Rice, or whatever more accurate model we want to decide to choose. And theta is the phase. Okay, so this is the received signal in the case of a frequency flat. Now let's assume the second hypothesis. The second hypothesis that the channel is time flat. Okay, if they were exactly time flat, that would mean that R of t does not depend on t, and theta of t does not depend on t. That's time flat. But we are considering an intermediate situation. Intermediate situation occurs when R and theta do not depend on time within the duration of a single waveform. So we have variations, we have fluctuation of the amplitude, but the fluctuations are not perceptible, are not seen within the duration of a single waveform. That's the concept of slow fading in our analysis. So we have fluctuation of the amplitude, but the fluctuations are not visible within a single duration of a waveform. This is slow fading. And consequently, we can write that the received signal is R, amplitude, e to j theta, the phase, that multiply x of t, so we have a complex random variable multiplying x of t. This input-output relationship is valid within the duration of a single waveform. From one waveform to the next, we have another value of this complex random variable representing the fading. So this is slow frequency flat fading that we are going to use for further analysis. If we assume, in addition, that we have coherent demodulation, and this is possible whenever theta, as usually occurs, changes slowly enough that we can measure the phase of the carrier and compensate for this shift, then we can remove this phase term and keep only the amplitude term, R of t. So slow fading, frequency flat, with coherent detection generates this very simple and yet very useful model for the received signal. The y of t, the received signal, during the time duration of a waveform is equal to r, a random variable, typically modeled as a Rayleigh or a Rice, that multiplies the transmitted signal by n. So it's a very simple model, you see. It differs from the additive wide Gaussian model just because we take into account this. A Gaussian channel is one in which this is a constant. Our fading model is one in which this r is a random variable. So that's it. That, on the other hand, the apparently innocuous introduction of this random variable changes quite a bit the number of considerations that we have to make for design, evaluation of performance, etc. So we are going to focus on this model and see what happens. So let me remember that this is the model. Y of t is equal to, is obtained exactly as in an additive wide Gaussian channel, except that the amplitude of the received signal is a random variable. The actual value taken on by R, the attenuation, is called the channel state information. So we immediately have we need a classification of the receivers because the actual value of R may be known or unknown to the transmitter or to the receiver. For example, the value of R may be unknown to the transmitter and to the receiver. So the transmission occurs as if nobody in the transmission chain knows the actual value taken on by R. Or it may be known to the receiver only. We can evaluate this by using pilot tone, pilot sample. So we transmit the data and we also transmit something deterministic so that the receiver is able to evaluate the amount of attenuation. A typical way of recovering channel state information, very simple and very typical, consists of creating a notch in the frequency spectrum, like this. So this is the frequency spectrum of signal that we transmit with a notch inside. And we fill up the notch with a known sinusoid, a pilot tone. Okay? So once we receive the signal, we may assume that the whole signal is affected by the same attenuation. Remember our assumption of a flat frequency flat fading, and consequently knowing the amplitude of the transmitted sinus, the pilot tone, and observing the amplitude of the received pilot tone, we know the attenuation, and consequently we know the value of R. So this is the case in which we may assume that the value of R is known at the receiver. In some cases it's unknown, for example, because it fluctuates so fast that there is no time to to do a reasonable estimate of it. In some other cases, the pilot tone may be known to the transmitter and to the receiver. The receiver measures the pilot tone amplitude and relays this information to the transmitter. Assuming that the value of R doesn't change that fast, we may assume that the channel state information is known to the transmitter and the receiver. And this, I mean, is not a classification with a theoretical meaning. It's a classification that has relevance because the performance of the system and its design will depend on the availability of channel state information at the receiver or to the transmitter. Okay, let's see how we can do demodulation or decoding in on a fading channel like that. Remember what we do in the Gaussian channel. We have seen that an hour ago. Gaussian channel, we do the following. We know that we have, for example, for 4 PSK, we know that these are the 4 possibly transmitted signals. Okay? And this is what we receive, Y, which is affected by Gaussian noise. So Y may come from this signal plus this noise, from this signal plus this noise, etc. So there are 4 hypotheses, and we have to choose the one that yields the minimum probability of error. And we know that the maximum likelihood, optimum, demodulation consists of, well, this is -1, sorry, that's inverse. the x hat is the value of x that minimizes the Euclidean distance between y and x. So in principle, we compute 4 distances and we pick the smallest. This is the smallest distance, and consequently our choice, the choice of the demodulator, will be the signal. Okay, this is what we know from a Gaussian channel. What do we do when we have a fading channel with the model that I've discussed like this? Okay, here we have taken into account 2 effects. Presence of noise, of course, and the presence of this R that affects the amplitude of the signal. Assume from now on that R is known at the receiver. So we know that the transmitted signal was an element of this constellation, the yellow point, the yellow area. We know the value of R, and consequently everything happens as if the transmitted signal were Rx instead of X. So everything is equivalent if we know the channel state information at the receiver. Everything is equivalent to transmitting over an additive wide Gaussian noise channel in which the original constellation do not consist of signal X, but rather of signals Rx. So we consider this shrunk constellation Rx. So we are Rx and N. And this is the effect of the channel, shrinking the constellation and adding noise. How do we do optimum detection in this case? Well, again, if we have channel state information at the receiver, then that we know the value of R, we can do exactly the same as we did for additive wide Gaussian noise channel. Again, this is the argument of the minimum. Optimum demodulation occurs by computing the Euclidean distance between what we receive and what we have possibly transmitted by taking into account the effect that the original constellation was shrunk by the effect of the multiplicative fading. So we compute the distance, at least in principle, we compute the 4 distances between y and the signal that have possibly been transmitted after multiplication by a factor of R. So this is the optimum demodulation with a fading channel like that we are considering, under the assumption that the channel state information is known at the receiver. Okay? Now let's compute the error probability. We repeat essentially the same calculations that we did for additive wide Gaussian noise by introducing the variation due to the presence of this amplitude. But once we have understood how we compute the error probability for a Gaussian channel, that's easy to understand how we do what we do for the fading channel by taking into account that now we are comparing y not with x but with Rx. What is the error probability for the additive Gaussian channel? Again, we define the error probability condition on the transmission of x. We upper bound this by using a sum of pairwise error probabilities. And then we say that the error probability is obtained by multiplying this by the probability of x, 1 over m, and summing over x. So the combination of these 2 formulas yields the union bound to error probability. Therefore, additive wide Gaussian noise channel. Remember that all this depends on the pairwise error probability, the probability that the received vector is closer to x hat than to x when x was transmitted. Now, fading channel. What we do is to follow 2 steps. The first steps consist of computing the error probability conditioned on the value of R. Okay, if we condition on the value of R, everything is exactly the same as with an additive wide Gaussian noise channel in which we have a known amplitude, a known attenuation. Condition with R reduces this channel to an additive wide Gaussian noise channel. So we can say that probability of error given the transmission of X and the channel state information R is upper bounded by a sum of pairwise error probability, again conditioned on R, where PE over R is 1 over m, like this. So it's exactly the same calculation as before, except that now we are computing error probability condition on the value of r, because this conditioning generates a model that is exactly the same as an additive wide Gaussian noise channel model. What is the pairwise error probability, the conditional error pairwise error probabilities? Exactly as before, the probability that y is closer to, now to rx hat rather than to rx. Everything works as if the constellation was made by signal rx rather than signal x. The unconditional error probability is obtained once we have P of E given r. To evaluate P of E, we have to multiply by the probability density function of r and taking the integral. So this is what we have. P of E is the expectation of P of E given r, and consequently we compute this, we multiply it by the density of the fading amplitude, and we integrate. That's it. So, 2 steps. First, compute the error probability for an additive wide Gaussian noise channel in which you have Rx instead of x. Second, take the expectation of that error probability with respect to R. And the nice feature of this procedure is that whatever approximation you may able to develop for a Gaussian channel can be easily translated into an approximation for the error probability for a fading channel. The only basic step is the only conceptually easy but computationally potentially hard step is the calculation of this average. How can we compute the error probability condition on the value of r, condition on the amplitude? Well, first compute the error probability over an additive wide Gaussian noise channel. This is a function of EB over N0, function of the signal-to-noise ratio. Then you observe that once the constellation, instead of being made by signal x, is made by signals Rx, capital Rx, then the energy that was EB originally becomes R square EB. So we take the expression of the error probability as a function of EB over N0. We change EB into R square over square time EB, and we have a function of R that we have to take average with respect to R, compute the expectation over R. So once you know how to compute the probability of error over additive wide Gaussian noise channel, the only thing you have to do is to multiply EB by R square and take the expectation, and we have the error probability. For example, consider binary antipodal signals. Over the additive wide Gaussian noise channel, the error probability is exactly Q, the Gaussian tail function, whose argument is square root of 2EB over N0. Okay, over fading channel, what do? Instead of EB, we write R square EB over N0, and we take the expectation. This expectation can be computed in its closed form, and but in a good approximation, it's very expressive of what's going on. With Rayleigh fading is that the error probability is approximated by this quantity, 1 over 4 EB over N0. And this is an important equation to start with in our analysis of what happens over fading channels, because we know that over the additive wide Gaussian channel, the error probability of binary antipodal signals decreases exponentially with signal-to-noise ratio. And the exponential behavior is reflected by this Q function. Over the fading channel, in particular with the Rayleigh fading channel, the error probability decreases only inversely proportional to, in a way, only inversely proportional to EB over N0. That is, the decrease of error probability is much slower with EB over N0 than it is over the additive wide Gaussian noise channel. And we can substantiate this claim by looking at the curves. Let's consider the 2 limiting cases, the Rayleigh fading channel over here and the additive wide Gaussian noise channel over here. You see that the slope of this curve is much smaller than the slope of the additive wide Gaussian channel. And in addition, the gap between the error probability over the Rayleigh fading channel and the additive wide Gaussian noise channel increases with increase in the signal-to-noise ratio. For example, 10 to the minus 4, you can see that, well, you have roughly 8 dB of signal-to-noise ratio necessary to achieve that error probability with additive white Gaussian noise, and you have, well, 10 to the minus 4 over here. You have 33 or something dB of for the fading time, for the Rayleigh fading. You have a gap of orders of magnitude in EB over N0 necessary to transmit over a fading channel. Order of magnitude in power that may not be supported by our system. We cannot say, okay, let's increase the power by a factor of 1,000 and we get the same performance. It may not be possible, especially for wireless transmission. So we need to close this gap in some way, and we shall see that coding is a way of doing this, a very effective way of closing this gap. In between the Rayleigh performance and the additive white Gaussian performance, we have the performance of a channel with rise fading. We have remember, a direct path plus some diffuse path. And as we increase the K, the ratio between the power of the deterministic component and the power of the random component, we see that we move from Rayleigh performance to additive white Gaussian performance. So in this case, Rayleigh performance is by far the worst. So we have two effects, the gap and the fact that the gap is increasing with signal-to-noise ratio. And we have to find a way of closing this gap. Repeat this calculation like this. You see that for different signal-to-noise ratio, we have different gaps, and the gap is increasing as we decrease the value of error probability. This is for uncoded. I mean, this is a calculation that holds for binary antipodal signal, purely a binary antipodal signal without any coding. We shall see pretty soon what happens when we are considering more complex signal. That is, we are considering coding in the signal space. Before doing that, we are interested in understanding what the channel capacity, what the limiting performance that we can achieve once we have decided to use coding possibly in a signal space. Remember that the channel capacity, the very definition of channel capacity is the maximum transmission rate and bit per dimension that we can transmit or with reliable, with successful transmission of information. Remember the capacity of the additive white Gaussian noise channel. Remember that bit per dimension is 1/2 logarithm of 1 plus SNR. In bit per dimension pair is a logarithm of 1 plus SNR. We can immediately, at least in principle, naive calculation shows what is the channel capacity with our fading model. Well, first of all, we have to assume ergodicity, and this is a very subtle point that I want to discuss in some detail. We have this fading model. Okay, we want to evaluate the capacity with this fading model. The calculation is, at least conceptually, very simple if we assume the so-called ergodicity. We assume that the fading channel is ergodic. What does it mean? It means that, first of all, the value of R, well, it's not exactly the definition, but anyway, conceptually, you may understand it by assuming that value of R is independent from symbol to symbol. Okay, you transmit one symbol, you have one attenuation due to fading, you transmit the next symbol, and you get an independent value of R. Code words are long enough so that a code word experiences all possible values of R. Okay, so we have a kind of averaging effect. In the Gaussian channel, it occurs because the code words are so long that they average the effect of noise. Here, we have to assume further hypothesis on the statistics of R is that the R changes independently from symbol to symbol, and the code word averages the channel effect. So symbol after symbol, all states, all values of R are experienced. In this situation, we have kind of self-averaging effect of the code word, so the code word experience all what is possible to experience in the channel. We say that the channel is ergodic. In this case, a code word in time experiencing all the states of the channel, and consequently we may exchange, as typical of ergodicity, we may exchange expectation with averages in time. And we say that the capacity in bit per dimension pair is equal to the expectation of the logarithm of 1 plus r squared SNR. We are simply observe that if the additive wire Gaussian noise channel has a signal-to-noise ratio SNR, if we multiply the signal by r, EB will be r squared EB, and consequent SNR will be r squared SNR. And then we take the expectation. So this is the channel capacity with an ergodic assumption for the channel with channel state information known at receiver only. I have another 3 slides, so I hope you won't mind if I go ahead for another 5 minutes. Now, what is the capacity? We take a look at the capacity for the Rayleigh fading channel with channel state information at the receiver, and we observe that these are the results. We may observe something that is striking at this point. After we have seen the error probability expression, we have seen a big gap between the additive wire Gaussian channel and the Rayleigh fading channel. Then we look at the capacity, and we discover that the difference between the capacity of a Rayleigh fading channel and the additive wire Gaussian noise channel is very small. I mean, for 4 bits per dimension pair, you see that the gap is about 2.5 dB, not much. Instead of 30, 40 dB that we have in the uncoded case, we have a gap like this. Well, intuitively, what does it mean? Well, it means that coding can be very effective for a Gaussian channel, because without coding, you have a big gap. With coding, the potential gap is reduced to a very few dB. That's important. What happens if we remove the assumption that the channel state information is known at the receiver? We may have other 2 limiting cases: channel state information unknown or channel state information known at the receiver and at the transmitter. With no channel state information, the situation is very bad. You see, this is the capacity Rayleigh fading channel with no channel state information. You see that now that we have a very big gap, at least for high enough signal-to-noise ratio, a very big gap between the performance with channel state information at the receiver. What happens if we have channel state information also at the transmitter? Well, you can understand intuitively that there is not much to buy, because the gap to close with addition of channel state information is not wide. So you add channel state information at the transmitter, we may close it partially only this gap. And this is what we see, what happens. We see that we have a small improvement for small values of signal-to-noise ratio, but for highest value of signal-to-noise ratio, there's very little to buy by assuming channel state information at the transmitter in addition to what we have at the receiver. Again, this in terms of channel capacity. There's a limiting situation in which you use an optimum code, etc., but they may not correspond to the practical situation. Practical situation, in a non-asymptotic case, you may have a considerable advantage of in having channel state information at the transmitter. Intuitively, how can you use it? Well, if you know in advance what amount of power, what amount of attenuation your transmitted power will be affected by, then you can compensate for it. If the channel is good, that's the concept of adaptive transmission. If the channel is good, or in other words, if the attenuation is small, then you transmit a regular power. If you have a large attenuation, a channel bad, then you increase the power. So you try to compensate the attenuation of the channel and try to transform the channel into an additive wire Gaussian noise channel. So in practice, for non-asymptotic case, the introduction of adaptive transmission with known center state information at the transmitter can be very beneficial. But we know that asymptotically for high signal-to-noise ratio, in terms of channel capacity, that may not be that beneficial. First, because the gap to be closed is not wide, very wide, and the second reason is that what we see from channel capacity calculation is that there is little to gain. We need to examine also the non-ergodic channel model, which is quite important in practical situations, but we'll do that. I assume that we have to finish at noon. Yes, so we stop here and we resume at 1:30 after lunch.